Hello everyone. What I'd like to do in this video here is give you two more examples of graphing polynomials. Start with the first one. Example. Let's try and graph p of x, which is equal to, let's say, negative 2x to the fourth minus x cubed plus 3x squared. Go ahead and pause the video and try to graph this for yourself first before we do it together. Okay, so the main things we need to look for when graphing a polynomial is we want to know the graph's end behavior, we want to know where the graph's roots are, where its x-intercepts are, and we also want to know where its y-intercept is. One of the big things we need to find are its roots, and to find its roots, we need to first factor this polynomial. That's usually the first thing I'm always going to try to do. If the polynomial is not already factored for us, we're going to want to try to factor it. Okay, so let's first factor. So I'm going to go ahead and look at these three terms. I'm going to see if there's a greatest common factor I can pull out. And it looks like I can pull out a factor of x squared. But what I'm also going to do is I usually don't like negatives on our leading term. And if I can, I'll usually try and factor that out. So I'm actually going to factor out a negative x squared. And let's see what we get in our parentheses. We're going to be left with a, it looks like a 2x squared minus an x. It's going to be a plus an x since I factored out a negative, and then minus a 3. Okay. So now what we want to do is we want to factor 2x squared plus x minus 3. Now there are a lot of different techniques for factoring polynomials of this form. In situations where we have the coefficient in front of x squared is not a 1, my favorite method is what's called the AC method. You don't have to use this method if you find a different method you like better. There's the box method, there's like a guess and check method. I like the AC method. So let's go ahead and do that. Can we see that right okay? All right. So what I like to call is the AC method. This is my method of choice. So we'll kind of do a little bit of, I guess, kind of a little aside here. Okay, so we're trying to factor 2x squared plus x minus 3. So what I'm going to do here is it's called the AC method. Remember, a polynomial in general is written as ax squared plus bx plus c. So what we're going to do is we're going to take the a and the c and we're going to multiply them together. So we take the a and the c and we multiply them together. So the a is a 2 and my c is a negative 3. And we get out a negative 6. So now what we're going to do is we're going to look for the factors of negative 6 that add to my middle coefficient, which is a 1. So what are the factors of negative 6 that add to 1? Some sort of combination of 2 and 3. All right, 3 and 2. And since it needs to be a positive, I need the 2 to be negative and the 3 to be positive. Notice when I add these together, if I add these together, I get out a 1. But if I were to multiply them together, I'm going to get out a negative 6. So what we're going to do now is we're going to split up the middle term. So we'll write this as a 2x squared. And instead of a 1x, how about we write that as a 3x plus a negative 2x minus 3. So what I've done here is I've taken this quadratic and I've written it so it has 4 terms. Notice that I really haven't changed anything. All I've done here is I've written this 1x as a 3x minus 2x. So I've just rewritten the middle of the term into a sum. So now that I've broken up this polynomial to have 4 terms, anytime you see a polynomial that has 4 terms, a technique to always try is factoring by grouping. So I'm going to group the first 2 terms together and the second 2 terms together. In the first set of parentheses, let's see what we can factor out. I think I can factor out an x. So we'll go ahead and factor out an x. And we'll be left with, what, a 2x plus a 3. And over here, what can we factor out? I'm going to go ahead and factor out a minus sign, or I'm going to factor out a negative 1. So if I factor out a negative 1, I'm going to be left with a 2x plus 3. Now, if factoring by grouping is going to work, whatever you have in these set of parentheses has to match. So I've taken this polynomial that had 4 terms, and I've broken it up to have 2 terms, and each of these terms has a common factor of 2x plus 3. So I'll go ahead and take that 2x plus 3, and I'll factor that up front. So we'll be left with a 2x plus 3 times a x plus a negative 1. You could write x plus negative 1, or equivalently, you could write x minus 1. So that's how I've decided to factor this quadratic. Okay, let's go ahead and write that up here. This may seem like it took a while, but once you get the hang of using the AC method, you can do it much quicker. So negative x squared, and this polynomial factored to 2x plus 3 and x minus 1. Beautiful. Okay. So now that we have in factored form, we can gather all the information we need to graph this polynomial. Okay, so let's first talk about maybe how about its end behavior. So end behavior, when we're trying to find the end behavior of a polynomial, recall that we just look at the leading term. So the leading term here, I'm going to write here the leading term is a negative 2x to the 4th. So the end behavior of this polynomial will look a lot like a negative 2x to the 4th. So a positive x to the 4th, or x to the 4th in general, looks like a quadratic, but since there's a negative out front, it's been reflected over the x-axis. So the end behavior for this polynomial, the end behavior is going to look like this. Okay, so I'll kind of write this note over here. So end behavior is going to look like this. Now the other piece of information we need to know is we need to know the roots. Okay, so when I'm looking for the roots, I'm looking for the x-intercepts. So I want to know what outputs, what values of x would I plug in to get an output of 0. Well, what we love about factored form is that the roots are screaming at us. So let's go over here and we'll make a list. Hopefully we can see that okay. Well, let's go ahead and write our roots. And we're also going to write the multiplicity. So roots and their multiplicity. Okay. Well, looking at this x squared term, notice if I plug in 0, that'll zero everything out. So 0 is a root. So x equals 0 is a root. I got x equals 0 as a root from this factor. This factor is being squared, so it has a multiplicity of 2. Okay, let's think about what value of x is going to make this factor 0. If you aren't able to see it, I'll show you in a second, but what should work here is a negative 3/2. So either you could spot that by thinking about what value of x would I plug in to zero this out. Notice a negative 3/2 would work if I plug that back in. Notice that the 2's would cancel, and I'd be left with a negative 3 plus 3, which will zero that out. If you don't like that argument, you could just ask yourself the question, when is 2x plus 3 equal to 0? And you could solve this. You could subtract 3 from both sides, and then divide both sides by 2 to get that x would be equal to negative 3/2. Okay. So that's how I got this root. Notice that this factor is being raised to the first power, so its multiplicity is 1. Similarly, it'll also have a root of 1 from this factor. So x equals 1 will be a root, and its multiplicity will also be 1. Okay, the last thing we're going to talk about is the y-intercept. So let's talk about our y-intercept. The y-intercept happens when our x value is 0. So what is the value of this polynomial when I plug in 0? Well, if I plug in 0 into this polynomial, notice I'll get an output of 0. Or if I plug in 0, this will get zeroed out, this will get zeroed out, this will get zeroed out. So the y-intercept is at 0, 0. 0, 0, or x equals 0 is actually also one of our roots in this situation. This won't always be true. It's something to always check. Okay, we have all the pieces. Let's graph this. Okay, what I always like to do when we're graphing polynomials is I always first like to write my end behavior. I kind of use these as a way to check my work. Because as I'm going, if things don't match up, I know I've made a mistake somewhere. So there's our end behavior. Looks like we have a root at 0. We have a root at -3/2. So let's write -3/2. We have another root. And we also have a root at 1. Let's move this over a little bit. We have a root at -3/2. We have a root at 0. And we also have a root at 1. Okay, so let's start at the root of -3/2. So at -3/2, it has a multiplicity of 1. So what we're always asking about the roots is, do I cross through a root or do I bounce off a root? And what we learned in the previous video is we could just look at the multiplicity. So since the multiplicity is odd, its multiplicity is 1, it's going to cross through. So it'll cross through. Now let's look at the root 0, x equals 0. This root has an even multiplicity, so it's going to bounce. So it'll bounce off of 0. Okay, so without even looking over here right now, just looking at this graph, notice that if my work is correct, I have to be able to cross through 1 to be able to match up with my end behavior. So for whatever reason, if I'm thinking, if I bounce off of this or if things aren't matching up, I've made a mistake somewhere. But let's go ahead and take a look at our root x equals 1. It has a multiplicity of 1. It has an odd multiplicity, so it's going to cross through and it's going to match up with our end behavior. Yes! So we know we've hopefully done something right here. Okay, so there we go. This is the graph of that polynomial. It looks like the McDonald's sign. It's making me hungry. Okay, so this is a rough sketch of this polynomial here. Now, just as a comment about these polynomials is I don't necessarily know the height of these humps. Again, all we really are wanting to do is draw a rough sketch of the general behavior of these polynomials. And this is a good enough sketch for me. I have my roots labeled. I have my y-intercept labeled. I clearly have my end behavior labeled. We're finished. Beautiful. Let's do one more example. Let's do a problem where it's already factored for us. Okay, so let's try to graph the polynomial p of x. Let's say it's -x times a x minus 6 to the 6th power, and then a x plus 2 to the 4th power, a x minus 1 to the 7th power. Am I going to run into that glare? Let me write this down a little bit lower. How about a little bit more to the left? So let's try to graph p of x, which is equal to -x times x minus 6 to the 6th, and x plus 2 to the 4th, a x minus 1 to the 7th, and an x plus 5 cubed. Okay. Go ahead and pause the video and try to graph this polynomial on your own. Okay. So let's first talk about the end behavior of this polynomial. So let's try to find its end behavior. So when we're looking at the end behavior, recall that we want to look for the leading term. So we want to hunt for what the leading term is. And what we do not want to do is you do not want to FOIL this out. That would be a nightmare. Please don't do that. Recall that we could actually quickly figure out what the degree of this polynomial is. I think from a previous example, what we could do is we could just add the exponents together. So we want to think that this is an x to the first power, so its degree is going to be 1 plus 6 plus 4 plus 7 plus 3. I'm just adding the exponents. So what are we going to get? 6 and 4 makes a 10, 7 and 3 makes a 10, I have an extra 1. Looks like I have a 21. So it's going to be a 21th degree polynomial. And notice I have a negative out in the front. So I believe if I multiply this all together, the leading term is going to be a negative x to the 21st power. Okay. So if I want to know the end behavior, its power is odd, so let's ignore the negative for a second. If you have an odd power, it looks a lot like a cubic. But in this case, since it's a negative, it's going to be reflected over the x-axis, so this is going to be its end behavior. Or I guess it's going to be, this will be the end behavior of this polynomial. Okay, so its end behavior is going to look like this. This will be the end behavior of this polynomial. Let's write this down a little lower. So the end behavior will look like this. Okay, let's look for the roots of this polynomial and the multiplicity. So the roots, let's scoot this over a little bit. The roots, and then their multiplicity. It looks like I'm going to get a root of x equals 0 from this factor, and it'll have a multiplicity of 1. Sounds like my daughter's having some fun out there. Looks like I'm going to have a multiplicity, a root of 6 here, and it'll have a multiplicity of 6. I'm also going to get a root of negative 2. Again, because negative 2 plus 2, that'll zero this out, it'll zero everything out. And it'll have a multiplicity of 4. I'll also get x equals 1 as a root, and it'll have a multiplicity of 7. And I'll also get that x equals negative 5 will be a root, and it'll have a multiplicity of 3. And the last thing we're going to look at is we're going to look for the y-intercept. Get this nice little table right here. So the last thing we'll think about is the y-intercept. For this polynomial, the y-intercept was what happens when I plug in x equals 0. When I plug in 0, notice that the output will be 0, which isn't a surprise because x equals 0 is one of our roots. Again, this won't always be the case. We have enough information to graph this. Okay. So let's write down our roots. So we have x equals 0 as a root. We have x equals 6 as a root. We have x equals negative 2 as a root. We have x equals 1 as a root. Let's do this one over. So here's negative 2. We have x equals 1 as a root. And we have x equals negative 5 as a root. Okay, let's draw our end behavior. And we're going to work from the left to the right. Okay, so we have to cross through, the graph has to hit the x-axis at negative 5. Does it cross? Does it bounce? Here's negative 5. Let's look at its multiplicity. Its multiplicity is odd, so we know it's going to cross through. Now, since it's coming from a factor that has an x plus 5 cubed, around x equals negative 5, the behavior of the polynomial is going to look a lot like a cubic. So while it will cross through, if you take a look at a graph of this, maybe in Desmos or on your graphing calculator, it'll have a little bit of kind of curvy action here, and it'll look a lot it'll look very similar to an x cubed right around x equals negative 5. Okay, what's going on at negative 2? Does it cross? Does it bounce? Well, at x equals negative 2, it has a multiplicity of 4, so it's going to bounce off negative 2. So it'll bounce. Notice right around negative 2, the graph looks very similar to a quadratic or something of an even power, and this negative 2 came from a factor that has an even power on it. Okay, the root x equals 0. It has a multiplicity of 1, so it'll cross through. And it'll cross through linearly. It'll cross through like a straight line, because think of something like x to the first power. That'll be something very similar to a line. X equals 1, it has an odd multiplicity, so it's going to cross through. It'll look a lot like an x to the 7th polynomial around 1, so it'll have a little bit of curvy action to it. Something like this. And then for x equals 6, it's going to bounce. And notice that we are hoping that it has to bounce because it has to match up with their end behavior. So if we're doing our work correctly, it has to bounce. And that's exactly what our roots are telling us here. The root is x equals 6. Its multiplicity is 6. It's going to bounce. So this is what the graph of the polynomial looks like. So p of x and x. And again, just as a comment, as we don't know the heights, the general heights of these humps here, we just want to draw a sketch that gives us an idea of the loose behavior of this polynomial. And this works for that. Beautiful. Hope you enjoyed these examples. We'll see you in the next video. Take care.